My name is Tina. Today I'm going to talk about multi-view flash and no-flash photogrammetry for shape recovery. There are various schools of thoughts for shape recovery using images. Two of the most well-adopted methods are geometric and photometric approaches. Geometric approaches such as structure from motion or multi-view stereo take images of a scene from multiple viewpoints, find point correspondences across images, and reconstruct the shape. Conventional geometric-based methods have fundamental limitations in recovering high-frequency details. Photometric methods, on the other hand, recover per-pixel surface orientation using shading cues. This approach typically relies on multiple images captured under different lighting conditions, which can be hard to set up. Given the complementary characteristics of geometric and photometric-based approaches, we aim to develop a method that combines both approaches to get the best of both worlds, aka a high-quality shape recovery. In this project, we present a multi-view photometric stereo pipeline that performs surface normal estimation leveraging minimal handheld hardware setup, consisting only of a monocular camera and a flashlight. We focus on implementing the closed-source method for Lambertian object shape refinement based on flash and no-flash imaging, and combining it with an open-source state-of-the-art structure from motion method. To evaluate our method, we develop a customized simulation pipeline in Blender for data capturing and ground truth generation. We also develop a handheld device for real-world data capturing to demonstrate the functionality of our method. We first capture a set of flash and no-flash image pairs at different camera views. Then we derive the rough shape through multi-view stereo using no-flash images captured at multiple views. We use learning-based descriptors like superpoint and superglue to extract them and match the features, and then we use CodeMap to reconstruct the coarse shape. Then we employ the flash and no-flash pair to refine the coarse shape. The core idea of normal refinement is to first compute a ratio image, which is the ratio of the no-flash image to the flash-only image, and then combine the ratio image and the image formation model to formulate a shading constraint. We use this shading constraint as part of our energy function of the normal vector for each pixel, and then we optimize this normal function to get the refined normals. Let's take a closer look at the image formation model. There are two shading functions, one for the no-flash image and the other for the flash-only image, which is just the flash minus the no-flash image. The flash-only image satisfies the n.l shading model, which states that the intensity at a pixel is proportional to the dot product of the surface normal at that pixel and the lighting direction. In the no-flash image, light rays reach the surface patch from multiple directions, and the reflected light becomes the integral over all possible incident directions. This integral can be linearized using second-order spherical harmonics into the form shown in the numerator of the top equation. We can then rewrite this equation into the shading constraint on the normal vector n, as shown here. Then we optimize the energy function, which contains three terms: the shading constraint, the normal constraint, which says the refined normal needs to be close to the coarse normal, and the unit length constraint. We evaluate our method both qualitatively and quantitatively using synthetic data. The two objects we use are Stanford Bunny and Happy Buddha, and for each object we capture 122 flash and no-flash pairs at different views. Qualitatively, the coarse normal map contains only a low poly geometry, while the normal map refined using our implementation contains slightly more details, as you can see in the bunny's face and the Buddha's sleeves. However, quantitative evaluation showed that the refined normal map has a higher mean angular error, and the exact cause of this unsatisfactory performance is unknown. But we've come up with multiple guesses and included an analysis in our report. We also tested our pipeline using real-world data of the boot, and we noticed that a refined normal have more artifacts than the coarse normal map. Considering the lack of smoothness of the refined normal map, one thing that could improve the performance is to include an additional smoothness term in the energy function.